Okay, welcome to video 2 for Systems and Objects Unit. Now, in the previous video, we talked about forces, and we said that forces are interactions between two objects. And oftentimes, this kind of comes down to a push or a pull. Now, we want to be able to represent forces, and on paper, we represent forces using things called vectors. So what a vector is, it's an arrow whose length represents the strength, and where it points represents the direction. Oftentimes, we call the strength the magnitude. So a vector is something with magnitude and direction. And that should make sense for forces because if a force is kind of like this push or a pull, well, then it has to have a strength and it has to have a certain direction. So how do we draw a vector? First, what we would want to do is set up a Cartesian coordinate system. The vector then, we could say, starts at the origin and goes at some direction. And the way I would label this, I would say this is a force, and I would put a little tiny vector sign above the force symbol just to show that this is a vector. So this is how we would draw a vector, and we would want to use a ruler to measure out its to carefully measure out its length, and a protractor to carefully measure out its direction. Now, we want to be able to make a diagram of forces acting on something. So this is a classic example. We've got a box sitting on a ramp. And I'm going to begin by making a force diagram. When you make a force diagram, you want to make sure that you label the forces where they happen. So the most common force we would have is the force due to gravity. It starts at the center of mass and always points to the center of a planet. So it would be vertically down in this vector. Also, there's something that's preventing this box from sliding down the ramp. That would be friction. I like to use a script F for friction. Now, this box is applying a force onto the ramp. So the ramp must be applying a force against the box. And this force that the ramp is pushing on the box with would have to be perpendicular to the ramp. And also, since the box is kind of leaning forward, it'd be a little closer to the leading edge of the box. So here we would have the last one. We call this the normal force. The word normal means perpendicular. So those would be the three forces acting on this box. We also have another technique called a free body diagram. In a free body diagram, you represent the object as a dot. Let's go and draw our Cartesian coordinate system. So we would have the normal force, we would have the friction force, and we would have the gravitational force. Now, notice I've kind of twisted my Cartesian coordinate system. So I would need to draw the gravitational force out at this angle. Now, what's really cool about this model is if we measure the angle of the ramp, that angle will be the same as the angle here between the negative y-axis and the gravitational force vector. So here we have the force diagram and the free body diagram. Now, let's say we have two forces acting on one object. Well, we would want to know what their sum effect is, or their net force. And to answer this, we need to use something called vector addition. So, get these out of the way here. Let's say we have our object here. And let's say that we have two forces acting on it. So let's say we tie two ropes to it, and we're pulling on these two ropes. Well, what direction would this object accelerate in? Someplace here, I would imagine, someplace up the center. We would want to be able to calculate that. Now, one technique we have is by taking the vectors head to tail. Now, one of the properties of a vector is once you draw it on a piece of paper, as long as you keep the length the same and keep it pointing in the same direction, you can slide it wherever you want to on a piece of paper. So if I were to slide this vector right up to here, notice that when I place these vectors head to tail, I have added those two vectors together. So the sum of these two vectors, here and here, gives me my net force, which I will represent with a sigma sign, because sigma means sum. Now, what's kind of cool about this is that the order doesn't matter. I could have moved my vectors like this. And notice that they're still head to tail. So when you wish to draw, or when you wish to calculate the net force of all the forces acting on something, one of the first early ways that I have to show you is, and this is called the graphical method, is to redraw all of your vectors head to tail. Carefully measure out their lengths, carefully measure out their angles, and put them all head to tail. And it doesn't really matter, it doesn't matter what order you place them in. This will work. Just got to put them head to tail. All right, now the final thing I want to talk with you today about in this notes will be the interaction pairs. Sometimes this is called Newton's third law. A force is an interaction between two objects. They always exist in pairs then, because object 1 is interacting with object 2, and object 2 is interacting with object 1. So for example, when you push open a door, the door pushes on you with the same force, and that is very counterintuitive. We would think that we're pushing on the door with a greater force because we see the door moving, but that's not the case. If you apply a 20 Newton force onto a door, the door is going to push back against you with the same 20 Newton force. And again, that's so hard for younger students to understand. Now, one thing I want you to notice is that for this to happen, all the forces must be on different objects inside the same system. Newton's third law only applies to internal forces within a system. So looking at this example here, we have a girl wall system. So as the girl applies a force on the wall will apply a force on the girl. So those are two forces within this girl wall system. Now I do have a warning. I do not want you to assume that Newton's third law is involved every time you happen to see two forces that happen to be equal in strength and opposite in direction. In fact, we're going to encounter many situations where we see two equal and opposite forces, but they're acting on a single object. A single object is not a system. So, any two objects or any two forces acting on a single object, they are not interaction pairs. Sorry about that, a brief little announcement. So when we have an interaction partners or interaction pairs, they must be acting on different objects because a system is a collection of objects. So if we look at this right here, here we have a system. This is the hammer-nail system. So what this means then is that the internal forces here, we would have a force of the hammer on the nail, and here we would have a force of the nail on the hammer. And I try to draw these vectors at the same length to represent the same strength. So notice that these two forces are in opposite directions, but they're equal strengths. So this would constitute Newton's third law. These are interaction pairs. However, when we come over to this, here we see that we have two forces that are in opposite direction and equal in strength. This normal force and this gravitational force do have the same magnitude. They are the same strength, and they are pointing in the same, or they are pointing in the opposite directions. However, what we have here is an object, not a system. This box is a single object. And because this box is an object, the normal force and the gravitational force are not forces or internal forces within a system. So this is not an interaction pair. So just keep in mind that Newton's third law only works for internal forces within a system. So there has to be more than one object. All right, this concludes our notes for this unit.